Cool. So now we're recording. So hey everyone, I'm Holly. I'm the co-president, if you haven't met me at all, alongside Alex. And so today we're going to have a nice fun little talk on electronics fabrication. So a lot of people know about a lot of like common mechanical manufacturing processes, especially when it comes to like sawing, drilling, cutting, things along those lines. Welding as well. Some of the things are a little bit more, I guess, niche, less known. So like knurling and peening, those are like certain surface finish processes and stuff along that scale. And so when you're like milling and turning, especially within these mechanical manufacturing processes, you can get down pretty small. So you can get down reliably within 5 thousandths of an inch. A lot of people within the machining world will label things by how many thou it is. So that's 5 thou. In reference to human hair, because this is really like the best comparison I could make, human hair is approximately 3 thou, 65 microns, according to my translation. Thank you, Google, for that good metric to material. So essentially, this is a very small scale. You can get very precise, but at some point, you can no longer get more precise than that. And so you have to start figuring out other ways of manufacturing and fabricating your parts. So what happens when your part can't be made using traditional machining? And the short of the answer is that it's a lot of chemistry and materials engineering. So just to kind of give you guys an idea of how small scale we're talking, this is the Intel Core i9 processor. It's 8 core, as you can see, divided up in this little diagram here. Can you see my mouse along it, or do I need to add a pointer?
I could see it, yeah.
Okay, cool. So this is kind of a breakdown of like how the entire thing is organized. Each one of these is a core. And so like, just like guessing, how small would you say this is, or how thin would you say these layers are? If anyone wants to guess.
Oh, you mean like how thick they are?
Yeah.
It's an i9, so 14 nanometers.
Nice. When we're talking how insanely small this is, this little like diagram on the right kind of gives you an idea of how small these are relative to wavelengths of light. And working down, like, I think it goes 1970 to about 2015 as far as what's encompassed here. And the scale goes from 10 microns, which translates to about 4 to the negative 4 inches, 0.4 thou, to the negative 7 inches. And so this is tiny. If you were to hold this flat and look at it, it would look like nothing was there. It is so thin. And so how do you even begin to develop something like that? That's beyond what you're able to machine off. That's beyond what the traditional manufacturing processes enable us to do. So we're going to look at some new processes. So specifically, we're going to take a look through all of these in this list. So we'll start off with some pattern transfer techniques, material removal, material addition, and ultimately doping. And like I said before, it's a lot of chemistry, it's a lot of materials engineering is what this comes down to. So first off, just to give you guys a background of what these are oftentimes processed onto, so to speak, is silicon wafers. And so depending on the diameter, these can be anywhere from like 200 to 700 microns thick. And they start off just from this little, oh my gosh, what's it called? this spool. And they get sliced down into these really thin sheets, these really thin wafers. And so once you have those wafers, you can do a lot of processes on them. And we're not limited just to silicon, but silicon is a very appealing material for the following reasons. I'm not going to go through all of it, but essentially like the mechanical, electrical properties are all extremely important. And especially as a semiconductor, it allows you to vary how conductive or resistive it is. So just a speed run through all of these processes for you. The first main one being lithography. Lithography is a pretty interesting process. It's essentially you coat something with a photoresist. There's two types of photoresist, and I'll go into that later. And you expose it to UV light. These resists are pretty sensitive to UV light exposure. And so what that does is it either hardens or softens the resist. And then you use a process to take that off. And so when we're talking about electronics manufacturing, you're working in a lot of layers, and there's a lot of seemingly like going back and forth steps. There's a lot of repetition just to build each layer. And so here on the right, you can kind of see what these two types of resist look like. There's positive and negative. And all that determines is whether the area exposed to the light is going to be washed away or whether it's going to stay. So there's some definite benefits and downfalls to each. Negative removes unexposed material. It's this one on the right. And so it has higher sensitivity, better adhesion, and is less expensive. However, it doesn't have as high of resolution. So positive photoresist, you can get really good resolution, better etch resistance, and better thermal stability. So it's kind of like a handoff of like, what do you need out of your process? As far as exposing these to light, you have to align it on some sort of machine, and there's different types of masks that you can expose it through. So the masks essentially are where you get your pattern for what's going to be removed or not removed, what is going to be exposed or not going to be exposed. So there's a few main types here: contact printing, proximity, and projection. Proximity is preferred to contact just because then it's not up against the wafer if you're using a wafer process. So you can use it a bit more. You're not having to worry about contact between the mask and the surface. Projection printing is good for, let's say you want to print something that's so small that if you were to shine light through the normal way, you can't possibly get your mask to have that small of a detail on it. So you can like kind of scale down through projection printing processes. Now, as far as applying photoresists, for wafers, they use a spin process. So essentially what happens is you start to get it up to speed. This photoresist that's dispensed onto here, it kind of works its way outwards and finds its way to the ends. There's different approaches to try to get this to be as even as possible. But ultimately your goal is to get resist of a certain thickness. Now on to the next step, etching. So what happens after you do that whole photoresist step? So etching is essentially just material removal. Instead of taking at it with like a facing tool, maybe you are doing a chemical wash over it. There's two types of etching. There's wet and dry. Their names are pretty self-explanatory. Wet etching involves like liquid chemicals. I believe hydrofluoric acid is a large component of that. And then dry etching, you're using things more like ion implantation, plasma, stuff like that. So with wet etching, the main thing to take away from this is that wet etching, you get this effect sort of like down here in the right side of the image. This is for an isotropic removal. And so what you see is that while this mask is here, when the etchant is removing material, it kind of digs underneath the mask a little bit. And that's a reason why dry etching would be preferred and why it can be used for smaller details. Wet etching is limited by 2 microns before like it starts to become a major issue here. And so if you want something smaller than 2 microns, you're going to have to start working with this dry etching process. And that gives us a cut that looks a lot more like this one on the left. Now, as far as applying material, there's 2 major types: chemical vapor deposition and physical vapor deposition. Chemical vapor deposition, it's using chemicals to add onto something. It's using those chemical reactions. It gives you this full infill here, as opposed to sputtering, which you're kind of applying, as the name suggests, sputtering onto the material. And then evaporation is a whole other process that's pretty similar, but slightly different. And I'll go into that in a second. So chemical vapor deposition, you essentially expose the wafers to some sort of gas that you want it to infuse with and react with. With sputtering, it's this weird machine on the left that it usually looks like. And so essentially what's happening is down here on the right image, you have a material. So let's say this is aluminum and you want it on your wafer. So what you do is you get a gas and you energize it into its plasma state. So argon is commonly used one here. And these argon particles, this plasma is directed into the, like I said, let's say aluminum. You can do it with gold as well, and directed onto the substrate material, onto the wafer. There's usually some sort of viewing port, so you can kind of see the plasma in there. It's pretty cool. And next we have evaporation. So the difference between evaporation and sputtering is that instead of charging these plasma particles and hitting off of the metal, you're just straight up evaporating the metal and hoping that it lands evenly enough on your wafer. I believe that sputtering is preferred generally, but evaporation is a pretty cool technique as well. And like I said, it's a pretty similar process, the difference being whether it's plasma or you're just heating it. Next, we have thermal oxidation. So oxidation is essentially, usually you're just like heating, say the silicon, and you're turning it into silicon oxide. And that oxide can be used for a few different applications as listed on the bottom. So it's definitely a beneficial thing to have. And it's another reason why silicon is so preferred, is because you can easily get the silicon oxide layer to act as a mask, insulating material, dielectric material, by that passivation. There's a lot of different applications. There's 2 main processes for this. There's wet and dry. And as I said before, wet implies you're using some sort of liquid. Dry implies you're using just a gas molecule, not molecule, gas atom. And the main difference between these is that wet oxidation, you have a faster rate, dry oxidation, you have a slower rate. That has to do with the water versus oxygen and how it interacts with the surface. Now for diffusion, this is especially useful if you're trying to change, you are changing the electrical properties of the region. And so essentially what you're doing is you're inserting atoms into the lattice of the wafer, into the silicon lattice, and you're creating essentially vacancies. And this will change the conductivity of the material. So this is essentially how you would change the conductivity of any semiconductor is by doping it. You've probably heard about this before. If you haven't, then you likely will at some point. And this is how you get like your PN junctions, if you've learned about that yet. So you're doping, and it's a similar process as the oxidation, where you're setting it into a furnace oftentimes, and you're inserting some sort of gas for it to be infused with. So knowing all of these processes, how would we get something like a PCB, let's say? And so we can kind of see how some of these processes get used into a final component. And so I'll just walk you through PCBs in particular. I would walk you through more, but I was kind of worried about how timing would work. So we can just walk through this. And if you have any questions after, we can go through that. So here we have your basic PCB. You can see how all of the layers are aligned. And there's a brief overview on the right. It's kind of small, but we'll walk through each step in detail. So first, you start off with that lithography step. I was able to find the best visuals for this whole process from start to finish on this link at the bottom. And they also go into more detail about each step as well, if that's something you're interested in looking at later. So you start off with inner layer imaging. So on the PCB, you have this inner layer and you want to get a pattern on it. So you get that pattern by using that whole process of putting a mask over it and exposing it to UV light. After that, you get a nice little pattern. And so you can etch, strip, all of that good stuff. Now you just have a material without photoresist on it. The stripping is just removing the photoresist after the fact. So then once you have that whole pattern out thing, you might let the layer oxidize a little bit, especially if it's like copper. They were saying it helps with the bonding. Each pre-preg layer is essentially carbon fiber, or sorry, not carbon fiber, fiberglass and resin. And it acts as an insulating layer, but it also allows for good bonding between each layer. These foil layers, you can see that they'll be etched away out after. But in the meantime, this is just getting us that nice little sandwich layer of a PCB board. So after you've got your sandwich, you can drill where you need to. And then they have this process called desmearing, where essentially you're just getting rid of some of that like extra film material that would be on there from the previous processes. And you can apply a layer of metal over it for that conductive region between layers. After that, you kind of go through that whole lithography step again of applying resist, exposing it, developing it, and then removing that extra material, getting your nice little channel there. You would go through another plating step after this, and this plating step essentially, you'll see in the next one, you have your copper plating initially. You can use something like tin after the fact. And that tin is going to provide a nice little protective layer for when you want to remove that top layer of copper. So now you have a copper channel as opposed to a sheet of copper with some tin over it. And then once you do that, you can strip the tin so that you just have this little copper channel. So we're kind of approaching the end stages of this whole process here. But essentially you add this soldering mask, which is this whole green film that you often see on your PCBs. And then you go through some final plating. I believe gold is nice here. There's some other materials that are commonly used. But this cross section, you can kind of see how it all comes together. And then lastly, you would just apply a silk screen. So that is where you get your labels as far as what each component is for. So your end product, you have your PCB board. And it looks very nice. You can get pretty intricate. You can do way more layers than this. You can get a PCB board that's like thick. You can get a really thin PCB board that's essentially just 2 layers. Ultimately, all it is you're connecting circuits without having to wire them per se. And so as far as design considerations, especially with designing for manufacturability, which is a huge thing, the big questions you're going to be asking yourself are, what tools are available to you and what properties are you looking for? Beyond that, there's some like extra steps you can take as far as like, how do I get a higher yield out of this? So yield is essentially like how much of your product is actually usable, because sometimes, you know, things just go wrong, especially when you're working at that scale. And so maybe if you're like, oh, I'm designing, you know, my little i9, I have an 8 core. Oh, one of the cores doesn't work when I'm testing it. Maybe I can sell it as a 6 core and just disable the 7th one. And of course, the overall cost, because time and money are key when you are spitting out products. Cal Poly has a few good resources if you're interested in looking more into all of this stuff. So as always, Robert E. Kennedy Library, you get access to a lot of good educational resources. There's also a class which covers micro and nano fabrication, MATE 430. It's cross-listed as BMed 434 and EE 423. And then there's also a microsystems technology group club. They're called MST, and they work in a clean room environment. So if that's something you want hands-on experience, taking either the lab for that class or joining that club at all, not to steal you away from AES, but if that's something that you want a particular experience, they do have that opportunity available to you. Do you guys have any questions about any of this? I know it was a lot, and I know I accidentally ran a little bit fast through it, so please let me know if there's anything you'd like me to look back at.
I was curious, one of the initial things you talked about was when you were comparing positive and negative photoresist, you mentioned about the sensitivity. And there were some other things in there as well. I'm curious if you can explain kind of what those, like what those are, in particular sensitivity, but also what the effects of the other things are.
Yeah, so sensitivity is essentially like, how long do I need to expose this to the UV light? Yeah, that's about as in depth as that get. Adhesion is between the hardened photoresist and the substrate, the board. And then for resolution, that's applying more to, I guess, like, so see how here you have this little key. So when you're exposing this to light, what may happen is like this edge is not going to be completely vertical. And so like trying to get it to be as vertical as possible is ideal, because then you can get really good features. And there's also, I think it's called chemically, I'm completely blanking on the name. Essentially, there's some things you can do if you're getting in depth to make those edges a little bit sharper as well. And then etch resistance. So you remember the etching process where either wet or dry, you're removing that material. So etch resistance, my understanding is that it's just applying to like, how long do you need to expose it to the etchant? does it wash away cleanly? Do you have to like leave it in for a bit, that sort of thing? Does that make sense?
Yeah, it does. I was particularly confused on sensitivity because I didn't know what kind of sensitivity, like whether that was engineering sensitivity kind of thing or
no.
Like that. Okay, gotcha.
Yeah, it's much more relative to like what the exposure. What the exposure's influence. Yeah. Is there anything else you want to look back at? All right, well, I'll go ahead and stop recording.